sklearn, feature extraction, text, TF-IDF transformer. Description. The TF-IDF transformer is a class in scikit-learn that transforms a count matrix of words into a matrix of TF-IDF features. TF-IDF stands for term frequency, inverse document frequency. It is a common technique in text mining and information retrieval used to weight words based on their importance within a document and across a corpus. Inputs. Term frequency matrix TF matrix. This is a matrix where each row represents a document and each column represents a word in the vocabulary. The values in the matrix represent the number of times a specific word appears in a document. Vocabulary. This is a list of unique words that appear in the entire corpus of documents. Outputs. TF-IDF matrix. This is the transformed matrix, where each row represents a document and each column represents a word in the vocabulary. The values in this matrix are the TF-IDF scores of each word in each document. Steps. Term frequency TF calculation calculates the frequency of each word in a document. This is simply the count of the word divided by the total number of words in the document. Inverse document frequency IDF calculation calculates the inverse document frequency of each word in the corpus. IDF measures the rarity of a word across the entire collection of documents. It is calculated as the logarithm of the total number of documents divided by the number of documents containing the word. TF-IDF calculation multiplies the TF score by the IDF score for each word in each document to obtain the TF-IDF score. This score represents the importance of a word in a document, taking into account both its frequency within the document and its rarity across the corpus. Metrics. Precision. The proportion of retrieved documents that are relevant. Recall. The proportion of relevant documents that are retrieved. F1 score. The harmonic mean of precision and recall. Visualization plots. Heat map. A visualization of the TF-IDF matrix, where the color intensity represents the TF-IDF score. Word cloud. A visual representation of the most important words in a document or corpus, where the size of each word is proportional to its TF-IDF score. Fine-tune parameters. Norm L1, L2, none. Default L2. L1 normalizes each document to have unit L1 norm. L2 normalizes each document to have unit L2 norm. None. No normalization is performed. USE-IDF Boolean. Default true. True. Use inverse document frequency IDF. False. Do not use IDF. Smooth IDF Boolean. Default true. True. Smooth IDF weights by adding 1 to document frequencies, as if an extra document was seen containing every term in the corpus. This prevents zero division errors. False. No smoothing is performed. Subline ARTF Boolean. Default false. True. Applies sublinear TF scaling, i.e. replace TF with 1 log_TF. False. No sublinear TF scaling is performed. Uncertainty methods. Confidence interval measures the uncertainty in the TF-IDF scores by calculating the confidence interval around the mean. Challenges and fixes. Challenge 1. Data sparsity. When dealing with a large corpus, the TF-IDF matrix can become extremely sparse, with many zero values. This can lead to computational issues and affect the performance of downstream tasks. Sample use case that resulted in Challenge 1. A corpus of news articles with millions of documents can result in a very sparse TF-IDF matrix. Fixes to Challenge 1. Dimensionality reduction techniques. Methods like principal component analysis (PCA) or singular value decomposition (SVD) can be used to reduce the dimensionality of the TF-IDF matrix by Identifying the most important features. Feature selection only keep the most informative features based on criteria like information gain or chi-squared statistics. Challenge 2. Overfitting. If the training data is not sufficiently representative of the real world data, the TF-IDF model can overfit the training data, leading to poor generalization performance on unseen data. Sample use case that resulted in Challenge 2. A training dataset consisting of only technical documents may not be representative of a broader range of text data. Fixes to Challenge 2. Regularization techniques. Techniques like L1 or L2 regularization can help prevent overfitting by penalizing large weights in the model. Cross-validation. Divide the data into training, validation, and testing sets to evaluate the model's performance on unseen data and adjust the model accordingly.